Section 9.3, Possibility Trees and the Multiplication Rules. So we're going to make something called a tree, which is a way of keeping track of all the possible events that might happen. And it's just a nice visual aid to help us keep track of things. So let's say we've got two teams, A and B, that are going to play each other until one wins 2 games in a row or a total of 3 games. So for example, if we have A, B, A, that would be one possibility. So first of all, let's just try and list that. How many ways can this mini tournament actually work out? So this is where we're going to make this tree. So we call this on the far left the root, that's our starting point, and our leaves are these terminal points. And you'll notice not all of them are going to go the same distance. Here I've got A on top, B on the bottom, just to kind of hit things easily. So if A wins the first 2 games, we're going to be done right away. That'll be a really quick one. But as you can see, we do have some that are quite a bit longer. And not only can I see how long, but I can follow this, if you can see where my cursor goes, and I can see exactly how that's going to play out. And so again, this is just a really nice way to visualize what's going on, the order in which something happens. I've got a lot of detail here. And again, we can then list those various possibilities out if we need to. All right, so we've seen that tree, we've seen that list, and so we're going to assume that all of those are equally likely. So then what is the probability that 5 games are needed to determine the tournament winner? So I've got my list here of how many games, and then I can count how many there are total, and if you count that list, we do have 10. So then how many of them require 5 games? Well, that are those 4 that are listed. So I get 4 out of 10, which is 40%. As we can see, the actual computation at this point is pretty easy. The hard part is actually getting all of my possible events and then my possible sample space. Let's look at the multiplication rule. So we've got a computer that has 4 input outputs, A, B, C, D, and 3 central processing units, X, Y, and Z. Any input output can be paired with any CPU. So how many ways are there to pair those? So again, I'm going to make a tree to try and help set this up. So here you can see I'm choosing A, B, C, or D, and then with each one of those I can pick X, Y, or Z. All right, now again, this one's a little bit more straightforward than what we had in the last one, but you'll notice we're going to end up getting 3 plus 3 plus 3 plus 3. In other words, 4 times 3, which in this case does get me 12 as my sample space. So here is that multiplication rule written out. So here we've got k steps, and we're going to say the first step can be done n sub 1 ways, the second n sub 2, the kth step n sub k, and so on. In which case the entire operation can be formed in n sub 1 times n sub 2 times all the way up to n sub k. So I'm multiplying k n's. So I have k number of multiplications there. All right, well, let's see what that's going to look like. Let's talk about pin numbers. So it's any sequence of 4 symbols, and here we're going to use the 26 uppercase Roman letter alphabets and 10 digits. Just to, we're not going to worry about upper and lowercase. Now, do note for pins, generally repetition is allowed. So what's it going to look like if we allow repetition? And here's just a quick list of some of the things that are possible. But as you can see, I've got 36 possibilities for 1, 36 for 2, 36 for 3, and 36 for 4. Again, 26 letters plus 10 digits. And again, there's a couple ways you can think about it. If we look at our multiplication rule, it's basically I'm multiplying 36 4 times. And as you can see, I get quite a large number there. That is over 1 million. Now, that's if we allow repetition. Let's say we say you're not allowed to repeat symbols. So if I pick A as my first one, I can't pick A for any of my other digits. So that means that I only have 35 options for my second choice. Again, I've got all the possibilities for the first one, but I'll now have 35 for the second, I'll have 34 for the third, and finally 33 ways to pick that fourth one. So this time, my multiplication rule, I'm going to multiply 36 times 35 times 34 times 33. I still get quite a large number, it's still over 1 million, but if we compare it to our previous number, it is definitely going to be a smaller number. Alright, my final question there then, what is the probability that a pin does not have a repeated symbol, assuming of course that all pins are equally likely? Alright, so basically these are using the two numbers we've got. That 1,400,000 is going to be the top number, that 1,600,000 is the bottom number, and if I do that probability, I get about 84%, and that tells me about 84% of pins have no repeated symbol. If you like to do computer programming, you could certainly set something like this up with a loop. Here is a general sort of example of how we might set this up. And again, we can always make one of these trace tables to kind of keep track of what's going on here. Here we're looking more at the 4 and 3, just to have a smaller set of numbers here to look at. Alright, let's talk about permutations. So permutation is we are now looking at not only the numbers, but the order in which we're putting them in. So for all of these, I have A, B, and C, but they're all in a different order. And that's what we mean by a permutation. How many different ways can I write these same symbols? Alright, so here let's have that little n as our generic way of doing it. And you can kind of see how we might have those steps to do that. Again, we've got n ways to do the first step, but there will then be one fewer in the second step. So in other words, there'll be n minus 1. And in general, the number of ways to do each successive step is going to be one less by each. And basically, we're going to end up doing n times n minus 1 times n minus 2, all the way down to 2 times 1. If you remember, that is our factorial definition, so n factorial. And that is our definition. So here we do assume that n is greater than or equal to 1. The number of permutations with n elements is n factorial. So let's say we've got the word computer, and I'm going to note there that all of those letters are different. How many ways can we rearrange them? Well, there's 8 digits, so it's going to be 8 factorial, which is 40,320. Now let's say we're going to limit this a little bit. We're still going to rearrange them, but the letters C and O have to be together in that order. So in other words, we're going to treat that CO as essentially a single letter because we're not going to move it around. In which case, I get 7 objects total. So I'm going to do this as 7 factorial, which is 5,040. And then finally, what is, if I rearrange them all randomly, what is the probability that those CO letters remain next to each other in order? Well, that is basically doing those two values I just did. I'll take that 5,040, divide it by 40,320, and I get 1 out of 8, or 12.5%. Alright, let's get a little bit more into detail about permutations. So here, I've still got 3 numbers, or 3 symbols I should say, but each one of them only has 2 permutations. I'm not using all 3 of them. We're going to call this an R permutation because I'm not using all of them. And we often denote this as P of n comma R. So I'm going to hop right to the formula here. We're going to take n factorial, divide it by n minus r, quantity factorial. So let's start with just a straight up computation. Let's find p of 5 comma 2. So that means I'm going to do 5 factorial over 5 minus 2 factorial. You'll notice I'm simplifying it out. So 5 factorial is 5 times 4 times 3 factorial, because I have a 3 factorial in the bottom, so I can cross them out and get 20. All right, how many 4 permutations are there of a set of 7 objects? So that means I'm finding p of 7 comma 4. So similarly, I'm going to set this up, and I'll end up with 840 as my answer. And finally, how many 5 permutations are there of a set of 5 objects? So here it's 5 comma 5. That means on the bottom, going to end up getting 0 factorial. Remember, we do define that as 1, and we can get that on our calculator if we forget. So this is just 5 factorial, which is 120. And that is everything in section 9.2.